Alright, hello everyone. So let's continue to discuss how we can use partial fraction decomposition to integrate a rational function. So we are in the case where we have a irreducible factor in the denominator. So in the decomposition, of course, we have a irreducible factor and we have a complication. So this is a complication from the previous video. So we are trying to extend the discussion from the previous video. So this is the rational function that you want to integrate. I have already given you the decomposition. Okay, I have found constants a, b and c. Okay, just to make sure, pause the video, try to figure out the decomposition by yourself, try to figure out the constants by yourself. Okay, so I'm not going to show you how I did that because we have already seen how to do that, and if I do, this video is going to be long. So I want to rather focus on integration. Alright, so we have the decomposition. So we want to integrate the left hand side. So it's same as integrating the right hand side. So let's integrate these three terms separately. So if you integrate the first, if you solve the first integral, so 3 over 4 x minus 1, if you integrate that, we can take 3 over 4 outside the integral. So we have 1 over x minus 1 to integrate, which is easy, a linear factor in the denominator, constant in the numerator. So the solution is natural log x minus 1, an arbitrary constant, let's say c1. Okay, c1 is an arbitrary constant. Perfect. Now if you take the second integral, 3 over 4 x plus 1, again super easy. We can take 3 over 4 out, just integrating 1 over x plus 1. Just like the previous integral, it's 3 over 4 natural log absolute value x plus 1 plus arbitrary constant, let's say c2. Okay, so the complication is the third one. Third integral, 3 over 2 x square plus 1. So let's take that 3 over 2 out. Now we have an irreducible factor in the denominator. And what did we do in the previous video? Well, I said, well, we have to split the numerator. We use a combination of integration by substitution and tangent inverse rule, right? But here really we don't need to use integration by substitution. Now why did we use integration by substitution? The reason is in the previous video we had a problem where in the denominator we have a second degree polynomial, in the numerator we had a first degree polynomial. Usually that's what happened, right? When you do the decomposition, you will have an nth degree polynomial in the denominator, and in the numerator we will have an n minus 1th degree polynomial, right? That's the relationship that we maintain in the decomposition. So it's super easy to use integration by substitution when you maintain that relationship. But luckily for us, in this particular decomposition, in the denominator we have a second degree polynomial, but in the numerator we have a constant. Why not we have a first degree polynomial in the numerator? Well, we had. Okay, so what's going on here is when you write the decomposition with like constants, like here a over x minus 1 plus b over x plus 1, and here it would be like cx plus d over x square plus 1, right? But when we evaluate the constants, what happened is it turns out that c was 0 and d was 3 over 2. So that's what happened in this particular problem. Okay, so that x coefficient of x term vanished. C is equal to 0. So rather than getting a first degree polynomial, we get a constant. So the rule is that you have an nth degree polynomial on the denominator. You can have up to n minus 1th degree polynomial in the numerator. Not necessarily an n minus 1th degree polynomial. You can have n minus 1 or n minus 2 degree polynomial. So but the maximum you can have is a n minus 1th degree polynomial. So maximum you could have in the numerator here is a first degree polynomial, but we end up with a constant. That's fine. Okay, all right. Okay, so now here we don't need to use integration by substitution because we can use the tangent rule directly. So here we have a constant over, so what is the tangent rule? It's 1 over x square plus a square. If you have something like this, the solution is 1 over a tangent inverse x over a, right? So here a is 1, right? A square is 1, so a is 1. So this is tangent inverse x over 1 is x plus arbitrary constant c3. So this is an easy complication, right? I mean, I guess I should have started with this problem before I saw the previous problem in the previous video, but it's okay. Okay, so the final solution, let's write these three solutions together. So 3 over 4 natural log x minus 1 plus 3 over 4 natural log x plus 1 absolute value of and plus 3 over 2 tangent inverse x, and arbitrary constant capital C. So let's choose capital C to be C1 plus C2 plus C3. Okay. Alright, so this is the solution for the integral that we started with. Okay. Alright, so this is a complication where really you didn't have to use integration by substitution. This is an easier problem. Okay. Alright, well, let's see another complication in another video. Thank you very much. Bye bye.